So today's little lesson here is about what happens when waves come into contact with each other or with something else. So it's about wave interactions. The three big topics we'll talk about today: the ideas of interference, reflection, and the construction of standing waves. So first things first. In terms of what interference is when any two wave pulses come into contact with one another, or when any two, full waves come into contact with one another. Interference is actually pretty simple to understand on a little sense, but when it gets more complex, it's a little harder to figure out what it is. But basically, interference is simply additive. So if you've got two wave pulses that come into contact with one another, if both of those waves have a positive amplitude, then the resultant wave will be simply the addition of the amplitudes of those two incoming waves. So you can kind of see that in this little picture up here on the top left here, that this little A plus B wave is approximately twice the height if A and B are both the same. That's called constructive interference when the resultant wave's amplitude is higher or larger than either of the incident waves. On the other hand, if the two amplitudes are opposite, one's positive and one's negative, then we call it destructive interference. The resultant wave is actually less. In this case, down here at the bottom, it's total destructive interference, where they're equal and opposite, so they add up to zero. It may not actually add up completely to zero, but any time where the resultant wave amplitude is less than the incident waves, we would call that destructive interference. So like I said, when you're talking about more than one wave pulse, the resulting wave patterns can get a little bit more complex. So in this little picture that's here, you can see there's a blue wave and a pink wave are kind of your incident waves. And they have slightly different wavelengths, slightly different amplitudes. And so when you add them together, and you could simply add them together point by point, you get that kind of green, fuzzy looking wave. It's got a slightly different shape than either of the other two. In some places, it's constructive interference. Some places, it's destructive interference. And when you've got a multitude of different waves coming together, like in sound or like in light, you can get all kinds of crazy patterns that come together, really complex looking resultant waves. But again, it's simply the results of constructive and destructive interference, additive interference. In terms of some applications of this, here's two simple ones. You've seen these before. That top left picture there of ripples in water. The light bands and dark bands that you see are simply due to the interference of light with the different thicknesses of the water waves. And so you've got, in areas of constructive interference, you've got a really bright wave band, and in areas of destructive interference, you have a dark, kind of a shadow in the water. And that's just a result of those two types of waves interfering with one another. Furthermore, down at the bottom, noise-canceling headphones, if you have any of these, they're really kind of cool. They have a way of sensing the wavelengths that are coming in from the outside. They auto-generate then an equal and opposite wavelength and try to cancel it out. They try to create total destructive interference to cancel out any of that outside noise. Pretty cool technology that they've got these days. All right, moving forward. Next idea is the idea of reflection. You guys know reflection with light. When you look in a mirror, you know what a reflection is. But any kind of wave, when it comes into contact with a boundary of some sort, will reflect. It may transmit as well, but there will be some sort of a reflection. So we've got two different circumstances over here. This is supposed to be, I guess it's a little girl, kind of a weird picture, but she's making a wave pulse in a string. And the string, and you can kind of see it over here, is sort of loosely attached to I don't know, a pole or a post or something along those lines. As opposed to the girl over here on the right, the string that she's flipping around is attached solidly to, say, a wall, something along those lines. This one on the right here is a little bit more like what we did in our Slinky labs, where someone at the far end of the Slinky was holding on to it solidly. So there's two different kinds of ideas. When we've got a wave reflecting from what they call a free end, in other words, that end is kind of free to sort of flip around loosely. When the incident wave comes in and it reflects, so you can see the incident wave's coming in here, here, here. Here's where it hits, and now it's reflecting. When it comes back, that reflected wave is on the same side that it was when it went in, so it's upright. As you saw in the Slinky lab, a different thing happens when it comes into contact with a solid boundary. And that's this picture on the right, what they call a fixed boundary. Here's that wave coming in, it smacks into the wall, and the reflection now is on the bottom. It's actually what they call inverted. So the type of boundary determines whether the reflected wave is upright or inverted. A free end will give it an upright, kind of the same shape that it came in. A fixed boundary will give it an inverted reflection. Same thing happens though when we're not just talking about one slinky, hitting a wall. If you have a wave passing through from one medium to another medium, in this case, the little pictures here show two different slinkies, two different springs with different densities. So you can imagine that the blue spring is a real heavy-duty spring, and the red spring is a kind of a lighter weight spring. When you have an incident wave going from heavier to lighter, you actually get, it's kind of like that loose end that we saw in the other video or the other picture there, that we get the reflected wave comes back. I'm not talking about the transmitted wave. The reflected wave here, when it's reflecting off of a lighter boundary, a less dense boundary, the reflection is upright. If we go from the lighter wave in this bottom picture to the heavier wave, it kind of acts like it's hitting a fixed boundary when it tries to hit that heavier object. And a reflected wave again here is inverted. So this can happen when light passes from air into water or vice versa, or when sound passes through a heavier and lighter medium, like from air through a wall or something along those lines. So the same kind of idea of wave interactions, reflections, occurs both at a solid boundary versus a boundary between two different media at the same time. So just a couple of things to give you some ideas in terms of reflection. That top left picture, that's the reflection that you all are probably the most familiar with, just reflection of light waves. But here's some other ideas of how reflection can work. For example, radar guns. If you've ever been caught, a radar gun actually functions by shooting radar waves off of your car, it bouncing back, and it can measure the time and the shift in time, so it can actually detect whether you're speeding and whether you're going towards or away from the radar gun. Down at the bottom, we can talk about sonar waves, either detecting a big school of fish like here, or the Titanic on the bottom of the ocean, that kind of stuff. Again, you're reflecting waves off of a different surface. And this one over here on the bottom right, that's echoes, basically. Echoes are simply reflected sound waves. So all four of these different images are simple kind of ideas of what reflection would be in a real-world application. Okay, our last topic here. Standing waves. Standing waves are kind of a unique phenomenon that you can see, and you saw these in the slinkies a little bit too. It's kind of this weird pattern that you get where it looks like there's this funky wave that's holding still, and this happens when you've got alternate patterns of constructive and destructive interference in a real regular repeating pattern. And it almost looks like, if you take a look at this picture down here, when you saw it in the slinkies, it almost looks like the slinkies playing jump rope, but you get these kind of series of areas in here where there's basically no slinky movement at all. Those spots are what we call nodes, and it's either the fixed ends or it's the spots in the middle where there's total destructive interference, where literally the slinky basically doesn't move up or down at all. The opposite of that is these spots here called antinodes, and antinodes are those regions of maximum constructive interference, where you've got the biggest flipping back and forth between the two. So a standing wave is a regular pattern where it doesn't look like the wave is moving, and it's characterized by nodes and antinodes. It's important to note that you can't just make anything into a standing wave. Standing waves can only occur in certain patterns, depending on where your fixed ends are. And so you can kind of see in the diagram here, you could imagine you're holding onto a slinky or, say, a jump rope. You can have the littlest, or the least, I guess, wavelength that you can have as a standing wave would be 1/2 wavelength. Only 1/2 of it. Remember, this is a full wavelength right here, where you've got a full crest and a full trough. So the longest wavelength that you could have, or the longest length you could have, would be literally 2 nodes, 1 antinode. The next way that you could do it would be this way, and that's that second picture, where you've got your wavelength is exactly equal to the length between the 2 ends. And that would be, so the length of the distance of the spring, I guess, would be equal to the total wavelength. And here you've got 1, 2, 3 nodes, 2 ends in the middle, and 2 antinodes, 1, 2. Then you can kind of do the same thing, where you could do a wavelength and a half would also cause a standing wave, or 2 full wavelengths would cause a standing wave. Any of these other circumstances over here, where you're not quite an exact multiple, is just going to cause sort of a chaotic looking interference. You're not going to see that standing wave. It has to be an exact multiple of half wavelengths in order to make a standing wave. Kind of a few interesting pictures here, and this is to wrap us up, this one in the next slide, kind of what standing waves look like. This top left picture is actually standing waves in a string that's vibrating. So you can see here's that half wavelength, whole wavelength, wavelength and a half, and 2 wavelengths, and that's actually just a vibrating string. This is actually how guitars and other stringed instruments, including pianos, work, is that they actually stand up, the vibrations in the string, what we call harmonics, is how those instruments make their characteristic tones. Up here, this is kind of a cool picture. They put some black dust onto a kettle drum and then hit the kettle drum. So this is actually a standing wave, a vibration wave, and this one right here looks a lot like this one in the coffee cup down below. It's a type of standing wave, two-dimensional, in a round environment. And these ones over here are different wavelengths that you can get from other types of pitches that you can kind of do variations on that. And the last one, this is the idea of the craziest idea of what a standing resonant wave would be. Most of you guys have had chemistry before, and you might remember the idea of orbitals, SPD and F orbitals. And it turns out that because electrons act like waves as well as acting like particles, the standing waves that they create, the resonance that they create as they vibrate around the nucleus, is actually a type of standing wave. And so we can say there's one shape called an S wave, there's a different harmonic, so to speak, called a P wave, or a series of P orbitals, and there's even a higher harmonic called the D orbitals. And so those are actually, at the subatomic level, an example of resonant or standing waves. So there you have it, the 3 basic ideas of wave interactions. You've got wave interference, wave reflection, and standing waves. Hope you enjoyed it. See you in class tomorrow.